We have seen how to solve recurrence relations using recursion tree approach. Just to remind you, recurrence relation are the relations of recursive algorithmic formulation, which are called from or which are generated from divide and conquer method, okay, where we recursively solve smaller subproblems of the given problem. Okay, so we'll see two more recursive formulation recurrence solving using recursion tree method. It's a very high level solving. I skipped some of the steps, but just to give you the basic idea. So this is Tn equal to 4Tn by 2 plus theta n. Okay, this means that there are the cost of algorithm is calculated as it has 4 different subproblems, each of size n by 2, and also a theta of n time cost for combining those subproblems or whatever with the solution. Now this thing can come like this, or it can come also like this, 4t n by 2 plus n. So you will consider this n is actually theta of n, and you can represent this thing like this. So it can come as like this or like this, and you can represent it like this, 4t n by 2 plus c of n. That means the cost of n you are representing with a real constant c. Now you will try to draw the tree. First step is Cn, and then there'll be 4 children, Tn by 2, Tn by 2, Tn by 2, and Tn by 2. 4 children each of size n by 2. Then we replace that with Cn by 2, the cost, and then we will have their children. Okay, so in that way we continue until we have one node in the in the subproblem, only one node. The size subproblem with size 1, we can say. So these are the leaf nodes of this tree. Okay, so we have to calculate the height of the tree, and the height of this tree can be calculated at n by 2 to the power I. Every stage is being divided like that. So at the ith stage it will be n by 2 to the power I equal to 1. Okay, so then I equal to log n to the base 2, which is called log n. Okay, so height is log n, and then so what is the cost of the sum of the nodes in the at this level? So every node takes theta of 1 time to execute whatever operation. So the total time is total number of equivalent to the total number of leaves, and in this tree total number of leaves is a to the power h. A is the number of children at every stage. Okay, this is a, and h is the height. So a to the power h is basically 4, because a equal to 4 here. 4 children at a time, 4 to the power log n. By the base change of logarithm formula, it will be n will come here, 4 will go there, to n to the power log 4, which is log 4 is log 4 is log 2 square. So this 2 will come down, so this is n square. So this the cost of leaf level is actually theta of n square. Okay, because as I said, each individual node takes constant time theta of 1. If you have 1 billion node of constant time, that's also constant time. But you have n number of node where n tends to infinity, then all this will be n theta of n square. This is actually n square nodes. So there are a lot of leaves here, and because every time it's getting divided in 4 parts. Now the cost at individual levels here, at this level is Cn, at this level is 4 times Cn by 2, that is 2 Cn. At this level it's 16 times Cn by 4, which is 4 Cn. In that way we keep summing up. Okay, this summation we have shown here. We take Cn out, and the parenthesis is 1, which is 2 to the power 0, 2 to the power 1, 2 to the power 2, in that way up to the log n minus 1. It should be log n minus 1 level. Okay, so whatever it is, this will become a constant. Okay, how big it is still a constant. A constant times Cn will still be theta of n when we remove the constants. Okay, you remember the asymptotic analysis will actually absorb the constants, and then this one is becoming theta of n square. Okay, so then this is theta of n square, theta of n plus theta of n square. We keep the higher order term. Okay, so the solution is theta of n square. Here what I'm trying to tell you, that see this theta n squared contribution is coming from this level, the leaf level. So there are two different costs, okay, root level cost, this root level, and then this is the leaf level. So the leaf level cost here is theta of n square. The root level cost is of the order of n, okay. Let's say it's theta of n. So when we sum this all up, this came to be the order of n. And but this side, the leaf side, came order of n square. So the leaf made more contribution to the cost. Okay, please understand this statement. Now see this another recurrence relation. So leaf is you can say contributes more. It's not contributes, it's more like incurs more cost. Okay, incurs more cost. Instead of contributes, I can write like incurs more cost. Here, so the incurs more cost, okay, the leaf. Now you see that this is another one, okay, recursive relation Tn equal to 4 Tn by 2 plus theta n cube, which is a combination, but it's n cube, so we rewrite it like that. We form the tree, and at every level, it's next level, because 4 subproblems, each of size n by 2. So this is a so at the height of the tree is still log n. Okay, so the cost at the leaf level is a to the power h, which is 4 to the power log n square. And at each level here, if we try to sum up the cost, this level is cn cube. At this level is 4 times n by 2 cube. Okay, n cube by 2. It doesn't really matter. It's how correct it is. If we miss something, or if we kind of we do not need to do it very rigorously. What I'm trying to show you is that at every level we sum up the cost, and it will form such a series, cn cube. Next level is 1, in the parenthesis 1 by 2 to the power 0 plus 1 by 2 to the power 1 plus 1 by 2 square. So this is like a decreasing series, you can see, decreasing arithmetic series, and its sum will be, this is actually 1, this one is 1, okay, and this when you sum up, it will become less than 2, okay. Whatever be the constant, you can see the leaf level is contributing theta of n squared cost, and as before, and then there's the leaf cost, this is the root level cost, or the upper level of the tree's cost, but now the root level is contributing more. So this is the final cost, which is the asymptotic of n square and n cube, is actually whatever is contributing higher cost. As we said, that's the basic idea of asymptotics. Whichever contributes a higher cost will be determining factor, will be the determining cost, because it's just asymptotic analysis. We just care for the highest growth rate function. Here the root is contributing the highest growth rate function, highest cost, and here the leaves are contributing the highest growth rate. So function, the final asymptotic cost is the leaf level cost. So here what I'm trying to tell you, please understand that in the recurrence relation, either the combination part or the recursive part, which breaks down into the leaves, either of them will contribute more cost, and whichever contributes the more cost in a final cost analysis, that will be the determining factor. Once we have shown two different trees where in this tree the major contributing cost is coming from the leaf level, and in this tree the major contributing cost is coming from the root level, n cube, and here this one is n squared, the leaf level. We are trying to generalize this kind of cases. So if you remember, there was one more case of the Mard sort where every level was having almost similar cost. Just let me try to show it quickly here. It was 2t n by 2 plus cn, okay, 2t n by 2 plus cn, t n equal to. So what we did, cn, then there are two kids, each cn by 2, and then cn by 4. So at every level the cost was actually same, cn, cn, cn. So how we find the cost? We found the height of the tree, okay, which was log n, and then we said total cost was Cn times log n. The nodes at the leaf level was theta 1 and a to the power h, theta 1 times a to the power h, which is a to the power log n. A is 2 to the power log n, okay. 2 to the power log n is is 1, okay, is n. 2 to the power log n is a to the power log n is 2 to the power log n equal to n to the power log 2 by logarithmic base change, which is 2 to the base 2 is 1, so that was n. So theta 1 n times was theta n, and this was theta n log n. So this was more than this, so that was the contributing cost, okay. Just to remind you this one. So there are three cases. One is where the leaf level contributes more. So this is, suppose this is case 3, okay. Leaf level contributes more. Consider this one, this problem where the root level contributes more. Consider this is the case 1, and this one where every level contributes almost equal cost. This is the case 3, okay, case 2, assume that. Okay, remember that 1, 2, 3. 1 is where root contributes more, 2 is where every level contributes same, 3 is where the leaf level contributes more, okay. Now let's see a generalization of this procedure using this recurrence relation where Tn equal to Atn by B plus Fn. This A is like this, okay, 4 here or 4 there. It can be anything, 1, 2, 3, 4, 5, 6. So it has to be greater than equal to 1, okay. And then Atn by B. N by B is like here, n is divided into 4 subproblems, each of size n by 2, okay. So it's n by B is like that. B has to be greater than 1. And because these are subproblems divided into the n is divided into different parts, plus Fn, which is the function to combine, which is asymptotically positive, okay. Fn greater than 0 for n greater than equal to n0 for sufficiently large n, okay. So that's why called asymptotically positive, that we already discussed when we are discussing theta notation, okay. Fn has to be asymptotically positive. That means Fn greater than 0 for n greater than equal to 0 for sufficiently large n. Now you see we draw the recursion tree for this recurrence relation. Fn is in here, the combination cost, then we divide into A subproblems, each of size n by B, okay. So we write Fn by B, and that way, all this time, A number of time. Then this is again being divided Fn by B square. In that way, all these 8 children will be divided into 8 more children of n by B square. In that way, it will keep dividing. So you can see at every level they are dividing in the at the same rate. It's not that one side of the tree is skewed. One side of the tree is being divided at a higher level than the other. So the tree will equivalently reduce to a problem size of 1. And at this level, what is the height of the tree? Suppose at n by b to the power I, this becomes 1. Okay, so then from here we can calculate I is actually log n to the base b. So that is the height of the tree. So how many leaves are there? A to the power h. Okay, a to the power height of the tree, a to the power log n to the base b, which is then by the base change of logarithmic formula. This h is the height of the tree we calculated. Okay, so n to the power log a to the base b. So this is the number of leaf nodes, and each of size each takes cos theta of 1. So together they will take theta of n to the power log a to the base b. This is the cost contributed by the leaf node. I can write it here, cost contributed or cost incurred by leaf nodes. Okay, cost incurred by leaf nodes. Now here so here there are 3 different cases which can happen. So now, like we did in the previous one, we will consider compare the cost contributed or incurred by the leaf level and the cost incurred by the root level. So if you see, if root level is higher, and then this will be kind of a decreasing geometric series. It will form a decreasing geometric series, and the cost will decrease from root to leaf. Okay, in that case, root will be the major contributor of the cost. Okay, that is the case one. That is the where okay, so let's consider where the cost increases when we go down from the root to the leaf. So that is the case one. Cost increases geometrically as we go down the tree. Okay, so which one have the major contribution of cost? So the major contribution will be the leaf. Okay, leaf dominates theta n to the power log a to the base b dominates. Okay, now consider the other case, case 3, where this cost decreases geometrically as we go down the tree. The cost is decreasing as we go down the tree. That means the root has more contribution over the leaves. So here we can say Fn dominates. Fn dominates. Okay, and the third case is that each level is roughly the same, like this, March-Sort recurrence relation, where each level contributes almost equal cost, especially at least the top level. At the lower level, when the nodes actually vanish, start dropping, if there's a unequal tree, that time we do not really care, but the major cost is contributed by most of the levels. So so the cost in this case will be Fn times the height of the tree, like we did here, Cn log n. That will be the major cost. So there is the height of the tree is being multiplied, and this is the Fn log n will be cost of the tree. So this is a theorem. I have actually shown you the proof of the theorem, relating it with some real examples, and I've shown you that in recurrence relation, either the root or the leaf contributes the major cost. If the root contributes the major cost, so that is the case 3. If the leaf contributes the major cost, that is the case 1. And then the case 2 is the from root to leaf, every level contributes almost equal amount of cost. In that case, we just take cost for any level and then multiply it with the height of the tree, and then we get the total cost. And whatever be the highest growing cost function, that will determine the cost of the time complexity of the recurrence relation, as this is the asymptotic analysis, and the highest growth rate function is the most important one.